Hello everyone. In this second video of linear algebra, we are going to talk about several topics, but they are all related to each other. And that is the Gaussian elimination and elementary row operations, then converting a matrix into the reduced row echelon form. Then we talk about the range space, the null space, the nullity, the relation they have to each other, span and linear independence, and rank of the matrix. So they're all related topics. So let's get started. One of the things that you might have heard is when you want to solve a linear system of equations, one of the methods to solve it is called Gaussian elimination, and the way you do it is using elementary row operations. So first of all, what is elementary row operation? Elementary row operation is if you have several equations written in several rows, you can switch the rows, you can multiply each row by a constant number, and you can add or subtract the rows. So let me show you an example here. Let's say you have two equations, for example. The first equation is like 2x plus y is equal to 4. And the next one is like x minus 3y is negative 5. Okay, so I have two equations or two rows, correct, of the matrix, because I can write this as a matrix of coefficients times a vector of unknowns is equal to a right-hand side known vector. Okay, so what can I write here? Well, the first row here should be the coefficients in the first row. If we arrange it basically in terms of x and y, order it properly, so you get 2 and 1. And the next one again are coefficients of x and y in the second row, so it is going to be 1 and negative 3. So if you multiply this coefficient matrix by that vector, you get the constant right hand side. These two are equivalent of each other. So you can always write a system of linear equations into matrix format. Good. So now one of the things you can do is the order of the two equations does not matter. So it doesn't matter whether your first equation is 2x plus y equal 4 or it is x minus 3y equal negative 5. So basically if I exchange these two rows, bring this guy up, bring that one down, it's not gonna change anything. And what does that mean about the matrix? So when we do the Gaussian elimination using the row operations, the elementary row operations, what we do is we form a, in this case, let's say a 2 by 3 matrix where the 2 by 2 part of it is the coefficient matrix, and then the right hand side of it is the constants on the right hand side of the equations. Okay. So this is how we basically combine these two matrices into this augmented matrix, and then we try to solve the system of equations. So as I said, if we swap the first row and the second row, all of it, right? So if I write it like this, for example, this is going to be the same equations, right? The answer is not going to be any different. The other thing is if you multiply a row by a constant, right? So for example, let's say if I multiply this whole row by a constant of 2, right? Then what would you get? So instead of this 1, you will get a 2, right? And instead of 2 times negative 3, you get 2 times that, which is negative 6, and instead of that you get negative 10. Again, the answer is not going to be any different. Okay, so you can multiply by any constant number any of the rows, and now you can add or subtract any of the two rows to each other. So for example, now that I have this, what can I do? What I can do is I can go ahead and subtract the first row and the second row, right? So second row minus first row. So if I call this row 1 R1, and then this is R2, of course, times 2, correct? This is what we had. Now what I do is I keep the first row, but instead of the second row, I say first row minus twice the second row. So I subtract these two rows of this new matrix, which has the same numbers. So I get 2, 1, and 4, and here 2 minus 2 is 0, negative 6 minus 1 minus minus 6 is 7, and 4 minus minus 10 is 14. Okay, so then I get into, sorry, this one doesn't need, so now I get into a form that is called Row-Echelon form. Okay, so as you could see, and I can do it for any matrix, using switching the rows sometimes, multiplication of the rows by constant, and addition or subtraction, because subtraction is a type of addition, correct? Just multiplying it by a -1, then adding them together. So I can get it into this format, where we call this row-echelon form. Now, what is row-echelon form? So in order for a matrix to be in a row-echelon form, you need all rows consisting of only zeros to be at the bottom. So if you have a row with all zeros, in this case we don't. In this case, no row is all entries of 0. So if there is such a thing like 0, 0, 0, it has to be at the bottom of this augmented matrix. In this case, we don't. So case 1 is taken care of. Then it says the leading coefficients of a row that is non-zero should always be strictly to the right of the leading coefficient of the row above it. By the way, that leading non-zero coefficient in each row, we call it the pivot of that row. So what does that mean? It means if I come here, and when I say leading, means from left to right. When you look from left to right, what is the first element in this row that is non-zero? You say, well, that's this one. Well, what about the second row? If you look at the second row, what's that? That's this number 7. Okay, so now if you look, this number 7 is strictly to the right side of 2, which is above it. So if the 7 was right below 2, that's not strictly to the right, it's below. Or if it was to the left of it, again, not. So it means, basically, if you have a 2 here in row number 1, right below it, you should not have any non-zero number. It has to be 0. If you have any non-zero number, it should start from the right side of the 2. It should start from here all the way to the right, which you can see that's the case. Correct? So row-echelon form means also, if you want to talk about it in another way, is if you look under each column, right, the non-zero element should be on the top of that column. Okay? Right? And let's say if there is another row, if I had a third row, this should be 0. Now, this should also be 0. And then if there was any other number that was non-zero, it should be here to the right side of this 7. Okay, so this form is called the row-echelon form, right? And I'll show you with more dimensions. But just wanted you to know about the meaning of row-echelon form. So this is now in row-echelon form. Now, there is a topic that is very related to it. Is called the reduced row-echelon form, or sometimes called the row-canonical form, that is very similar to the row-echelon form, but with something extra. So first, it has to be in the row-echelon form, but then the leading entry in each, the pivot basically, should be 1. The pivot should be 1. And then if you have each column containing a leading 1, has to have 0 in all other rows. Okay, so if I go back here, you see when I look at this first column, it has a non-zero number here. Anything below it has to be 0. It is. So I'm good. Okay? Now, but if you look at the pivots, this is 2, this is what? 7. So this is still not reduced row-echelon form, okay? This is just row-echelon form. So if I want to reduce it, then what should I do? whatever I have here, correct? So first, you saw I multiplied by a 2, then I subtracted, and let me just call this 2 times the new R of 2. So here when we say R1 or 2, I'm referring to the new matrix. What should I do here to convert that 2 and 7 to 1? I have to multiply again the new rows by a constant number. So I'm going to multiply first row by a 1/2. That makes that 2, 1, 1, 1/2, and 4 to be 2. And this row that has a 7, I multiplied by 1/7. So that makes this 0, makes this 1, makes this 2. So now you have the reduced row echelon form where the pivots are 1. It is in row echelon form, and again, if you look at the third law, it says each column containing a leading 1 has a 0 in all other entries. Has a leading 1. So this one that has a leading 1 should have 0. What about this column? No. This column does not need to have a 0 below because the leading element is not 1, it's 1/2. Only the leading ones should have all below them a bunch of zeros. Non-unity numbers they do not need to have all zeros below them. Okay, so, and when here it says leading, so for a column, leading means it is on the top, and when it talks about a row here, it says leading, it is on the left. Okay, so hopefully now the meaning of elementary row operations or Gaussian elimination, as well as row echelon form, reduced row echelon form, or canonical form, and pivot are clear. And why do we do all of that? Because now I have converted my system of equations into a form that much easier to solve, right? If I go and rewrite it back into the XY form, so remember the first row has to be multiplied by x and y, so you will get x plus 1/2 y is equal to 2, and then here is 0x plus 1y is equal to 2. Okay, so now you have one of your numbers already set, and then you plug it right into the next one, and that will give you what? This is 1 of, this whole thing is going to be 1/2 of 2, which is 1. Take it to the other side, and x be 1. Okay, so this way that you have one of the variables, and then you plug it back into the previous one to get you the next one. If there is more, again, you keep doing that. It's called backward substitution. Okay, so when you reduce it into reduced row echelon form, now the solution of it is very easy. You have one of them, and then by plugging it back and everything back all the way to the top, you can get all of your variables easily calculated. Okay, so it's called backward substitution. And this is not just what you do to solve a system of linear equations. Later I'll show you. You can use this method to find inverse of a matrix, and it has so many other advantages. But for now, not only, as I said, we can solve a linear set of equations with it. Later, we're going to use it to determine what? The rank of the matrix. Okay? So this reduced row echelon form is actually a very commonly used and useful operation in matrices. And by the way, in MATLAB, there is a command RREF, reduced row echelon form, that you can apply. So if you have a bigger augmented matrix, let's say your matrix is, let's say you have 4 equations and 4 unknowns, and the coefficients are 1, 3, 0, 2, then 9, 7, -4, and 2, or let's say 3, and then 0, -2, -1, 8, -5, 4, 7, -1, correct? So this is your coefficient matrix, and then your right hand side is equal to, let's say 1, let's say 6, -7, and -5, right? So your augmented matrix is going to be A side by side by right hand side, and then you can say augmented matrix reduced row echelon form is equal to RREF of the augmented matrix. Okay, so let's run this, see what you get. Okay, so now if you look, this is my set of equations. The first part of it, 4 by 4, is the coefficient matrix. This is the right-hand side. And when you make it into reduced echelon form, you clearly see that. Actually, not only this one gives you the coefficient matrix as an upper triangular, it gives you actually as a diagonal. So it directly gives you the solutions. If you look, the last variable is this number, the third variable is this number, the second one is this, and the first one is this. So basically, it gives you a lot better than a simple upper triangle. Because if you look here, your coefficient matrix, right? After this reduced row echelon, your coefficient matrix is upper triangular. But when this one command is applied, it gives you actually a diagonal with all ones. So it is a little bit more than what we do, right? And you can see back here, if we go and look at the documents for it, you see that the reduced is the Gauss-Jordan elimination. So it's not just the Gaussian elimination, it's the Gauss-Jordan elimination. Okay, to basically make it what? Make it a diagonal. So that's the difference between Gaussian elimination, right? Gaussian elimination gives you what? Gives you an upper triangular matrix for the coefficient. But the Gauss-Jordan elimination converts this into just what? All one, and this guy also take care of it. So how does it do it in this case? If I don't want to stop here and I want to go to the Gauss-Jordan elimination, what should I do? As you know, I should get rid of what? This 1/2. So what do I do to get rid of that 1/2? So this is a 0. Whatever number times that 0 I add to 1 is not going to affect anything. So now that I have this, I need to get rid of this 1/2 using this 1. So I multiply now the second row by a negative 1/2 and add it to the top row. Correct? If I do so, right? Then this guy becomes negative 1/2 plus 1/2 becomes 0. So now what I do is I keep the second row, but for the first row I do R1 minus 1/2 R2. And so 0 and 1, it's going to stay at 0 and 1, but that is going to be 1 and 0. And then here, so it's going to be 2, and negative 1/2 of that minus that is going to be 1. Right? And clearly this means your x is equal to 2 and your y is x is equal to 1 and y is equal to 2. So if you go one step further and make it basically an identity matrix like this, right? Their coefficient matrix is now an identity matrix. This step or this format is called the Gauss-Jordan elimination. And when you put your set of equations in that form, you do not need to do the backward substitution anymore, because that directly gives you out of the variables. Okay, and this is the one that we use to find the inverse of matrix. So that was good. At least we know now the difference between the Gaussian elimination and what? Gauss-Jordan elimination. Yeah, so although I didn't want to talk about it, but kind of the MATLAB command forced me to talk about it. Good, that's good. So we learned something extra, right? So we can add it to our Gaussian elimination. And then what? Gauss-Jordan elimination. Good, and we learned also about the pivot and reduce row echelon form and everything. Good. So now that we learned about all of this, now we need to talk about the range or the column space, the row space, linear independence, span, rank, and so on and so forth. Okay, so we say a bunch of vectors u1, u2, all the way to un are linearly independent if and only if the linear combination of them is equal to vector 0 when and only when the coefficients are all 0. So no other non-zero combination of these coefficients, right? So let's say even if one or two of them are non-zero, when you combine linearly, will end up to a vector 0. So for example, if I have vector u1 equal to, let's say, 1 and 3, and if I have vector u2 to be like, let's say, 4 and 12, then these two vectors are not linearly independent. Why? Because I can say negative 4 times u1 plus u2 is equal to what? To 0, right? And by 0 I mean 0 and 0, of course. So you see, there is a linear combination with non-zero coefficients available, which can give me a vector of zeros, and that means these two are not linearly independent. And clearly that's the case, because if I multiply this by just number 4, that's going to be the second one. So when one of them is a multiple of the other, they are not independent. But this is easy when it's just two of them. When you have 3 or 4 or 5, now it's, of course, if one of the vectors is a multiple of any of the others, that's over. But sometimes it's not as easy, so you have to add several of these vectors in a linear combination to get another one. Okay, so when you have more than two vectors or two components in general in the vectors, it's not as easy, right? So you might have something like this: u1 equals, let's say, 1, 2, and 4. And then u2 to be equal to 1, 3, and let's say 5. And then u3 to be something like, let's say 3, and then 8, and then 14. Okay, so now clearly none of the columns is a multiple of any other. But here, if I basically say 1 times u1 plus 2 times u2 is equal to u3. So a linear combination of 2 will make the third one. Now here you can bring this ut to the left hand side and say what? Minus ut is u3 is equal to 0. So again, you found a linear combination with non-zero coefficients, which gives me a vector of what? Zeros, without all of the coefficients being 0, so it means these three are what? Linearly dependent. When there is no way to do so, let's say all I need is to just change one of these numbers, just make this like 10. Now I cannot combine these three in a linear combination like this without having all three of these guys to be 0. Of course, when I multiply all of them by 0, I will get a 0. But any other combination is impossible. Then we say these three are what? Linearly independent. Okay, so that's the meaning of linearly dependent and independent. Now, what does it have to do with the matrices? Well, one thing that you can determine whether these rows are linearly independent or not is to form a matrix using them, right? So what you need in this case is you say, well, I'm gonna make a matrix like A, which is these 3 column vectors augmented into a 3 by 3. Okay, so you combine them into 1, 2, and 4, 1, 3, and 5, 3, 8, and 10. Okay, and then the number of basically linearly independent column this matrix has, by the way, we call it the rank of the matrix. So let's talk about it right now. So the rank is how many of these columns or how many of these rows does this matrix have that are linearly independent. So if I find the answer to that, that's also the same as, of course, the number of independent vectors. And how do I do it? Well, using that reduced row echelon form. If I can reduce this guy to the row echelon form, that will tell me how many independent columns or rows I have. So how do I do it? Well, in this case, first I need to basically convert these two elements. So we start with the first column and try to get these two elements into 0. So if I call them row 1, row 2, and row 3, then what I need to do is to keep row 1, but for row 2, I subtract 2 times row 1 from it, and row 3, I subtract 4 over 1 from it. And so you will get 1, 1, 3, and here you will get a 0, you will get a 1, and you will get a 2, and here I will get a 0, I will get a 1, and I will get a negative 2. Okay, and now I can proceed one step further, and now that this column is in the reduced row echelon form, now I go to the second column, and I need to just eliminate this one, and for that I just need to subtract the second row from the third row. So it's just like R3 minus R2. And you will get a 1, a 1, and a 3. You will get a 0, 1, and a 2. You get a 0, 0, and negative 4. So now it is in reduced row echelon form, except for this negative 4, right? And if I want to, I don't have to, but if I want to, I multiply the last row by negative 1 over 4 and make this last element also 1. But this is just enough, if you look at it, this is just enough to tell me that the rank is 3. Why? Because if I look at my rows, there is no row left that has all zeros. If you end up with the row of all zeros, that means you have what? You have only 2 independent, linearly independent rows. The last one was depending on the other, so I could eliminate it to be a bunch of zeros. If I get 2 rows at the bottom with all zeros, it means out of the 4, let's say, 2 of them were depending on the other, so you only have 2. So rank of the matrix is going to be what? Is going to be basically the number of rows that you originally started with minus the number of rows at the end of the matrix, at the bottom of the matrix, where has all what? 0. So if I want to write it very clearly, rank of this matrix m by n, which has m rows, is equal to m minus what? Minus the number of 0 rows, and by 0 rows I mean all entries of it are 0, at the bottom of the reduced row echelon form of A. Okay, that means that those numbers of rows are not linearly independent from the other. So this is one of the methods for calculating rank. There are other methods like the MATLAB command. If you go and look at the rank command, so the rank command in MATLAB is basically calculating it. If you go and look at the explanations, it says the method is using what we call singular value decomposition, which is a little bit more time consuming, but the most reliable. So we get to the singular value decomposition in one of our future videos, okay? This is like a generalized version of eigenvalues, singular values. So we get to this, but in general, one of the simple ways is this reduced row echelon form, okay? Which can tell you the number of independent rows. And so that entity we call the rank of the matrix. So I explained the notion of the rank for you. And by the way, if a matrix does not have full rank, we call it rank deficient or singular. So definitely, what's the rank of a matrix? If your matrix is m by n, right? So if your matrix is, let me continue here. You have a matrix with m rows and n columns, right? Between these two numbers, one of them is less than the other one, correct? So the rank of clearly A is the minimum of m and n, right? The smaller number of the two, you might say it's just equal to the number of rows, assuming the number of rows is less than columns. So that's rank of A, and if it is, this is the maximum of the rank. This is not the rank always. This is what? This is the rank of A max. This is the maximum rank that it can have. If that's the case, we say what? We say A is full rank, which means it has all rows or columns that can be linearly independent. It has all of them. If it is such that the rank of A is less than the minimum of m and n, right? Let me write it this way. If that is the case, then we say A is what? Is rank deficient. Or singular. Okay, so that's the meaning of a matrix that does not have all possible linearly independent rows or columns. We call it rank deficient or singular. Okay, so I explained the notion of rank deficient and or singular for you. Good. Let's see. So I just underline whatever I cover for you. Now, let's talk about another thing. So here you see I specified the definition of rank. Rank is the dimension of row space or column space of a matrix. So now here we have to talk about what? Row space or column space and the fact that they are equal. So what does that mean, row space or column space of a matrix? Well, your matrices are not always a square, right? Many times they are non-square or we call them rectangular. So let's say, for example, you have a matrix A that is like 2, 3, 4, 1, 6, 0, 7, 8, negative 1, 5, negative 2, and negative 6. So here your matrix is a 3 by 4. So the maximum rank it can have is 3. Good. Now what is row space? What is column space? The space spanned by all the rows of the matrix is called the row space. Okay, so if I call them, let's say R1, R2, and R3, the space I can span by these 3 rows is called the row space. And now you might say, what is a span? That's the good question. Span means any possible linear combination of R1, R2, and R3. So here, when I say span, or I say row space, let's say, as I said, row space of A is equal to span of R1, R2, and R3. And what does that mean? It means any possible combination, any linear possible combination of these three. So anything, any vector, it means any vector u that can be written as C1R1 plus C2R2 plus C3R3. Okay, the space of vectors u, which is any possible linear combination of these three rows, that space is called the row space of A. Similarly, I can define what? I can define the column space of A, which is the span of the columns of A. So here, if I go ahead and call these columns C1, C2, C3, and C4, right? Then it is going to be the span of these four columns. So it means any vector W, let's say, which is a linear combination of these guys. So by the way, I call them C and C. So to avoid confusion, let me change the name of these coefficients. So I call them K1, K2, and K3 to avoid confusion. So K1, K2, K3 are scalars. So it is like K1, C1 plus K2, C2 plus K3, C3 plus K4, C4. Okay, so clearly you see the nature of row space and column space is a little bit different, right? This is, in general, the vector W that you have is a combination of 3 by 1. So the dimension for this vector W is going to be a what? A 3 by 1. While here I'm combining 4 by 1, 1 by 4, all of the rows, so it is going to be a 1 by 4 type of vector. So the row span and the column span are different, okay? They are not exactly the same. But if I go back all the way, the dimension of these two spaces for both of them is the same, and that is called the rank. So when I say they are equal, I don't mean the row space and column space are equal. The dimensions of them is the same, and that common dimension, and there is a lot of proof behind it why they are the same, but the common dimension of these two spaces is called what? The rank. So it doesn't matter that one dimension is bigger than the other, right? One of them is a 1 by 4, one of them is a 3 by 1. If I look at the dimension of the space spanned by the rows or the columns in both cases, if they are all linearly independent, the rows or the columns, the max dimension between row space and column space for this case is going to be 3. You will never get the dimension of any of those, like for example the row space, to be 4. It is not going to be possible. Why? So in this case, it might be kind of clear why the dimension of this is at best 3, because all of these vectors are 3 by 1. So the space formed by C1 to C4, or any combination of them, is going to be a 3D space, correct? So the dimension, let's say, the dimension of this column space, the max of it can definitely be what? 3. When is it max? When these columns are all linearly independent. What about this case here? So you have a 4D space, right? Because you have R1, R2, and R3, but the problem is you're only using 3 vectors in that space. So whatever you do in that space, one of the elements is definitely going to be depending on the 3 others, okay? Because if you had a 4th element, so you could say K4 times R4, yes, now you can have a 4D space. because you have 4 elements in each one of them, and in general all 4 of these could be linearly what? Independent. But in this case you only have 3 of them. Since you only have 3 of them, the 4th element in this space is going to be depending on the 3 others, and dimension means the independent parameters. So although here I have 4 by 1 by 4 vectors, since I only use 3 of them, still the dimension max in this space is going to be what? Is going to be 3. Okay, and the same for the bottom one. I have 4 vectors, but only 3 of them can be linearly independent. This 4th one will depend on the rest of them. That means, again, the max dimension is 3. As I said, there is a lot of proof behind this. I don't want to get into depth and detail of that, but just in general, know that for a rectangular matrix, the rank is, max rank is what? Max rank is the minimum of the number of rows and number of columns. And the dimension of the row space and column space are equal, okay? So here, let's look at one example. So here is my 3 by 4 matrix, and now in order to get the rank, I perform the elementary operations, row operations. So what I need is, since this guy is already 1, it's good. I need to just add row 2 to row 1, and then subtract 3 times row 1 from row 3, and that coefficient 3 comes from 3 over 1, just negate it. And this 1 times R1 also is the ratio of negative 1 over 1 negated. So it is 1, 2, 4, 3. You get a 0 and a 0 here. And then you get a 2, a 6, a 4, and then negative 8, negative 13, and negative 4. Okay, and now I need this element, the leading element in this row, to be 1. So first I multiply the second row by 1/2 to convert it into a 1. And the first row is intact. The third row is intact. Now I try to eliminate basically this element, and all I need is to add 8 times row 2 to row 3. And again, this 8 coming from dividing negative 8 by 1 and negating it. So if I do so, I will get 1, 2, 4, 3, 0, 1, 3, 2, 0, 0, 11, and 20, I assume. Okay, now how many rows with all zeros do I have? Nothing. Every row has a non-zero element in it, so clearly rank is 3. You see the rank cannot be 4, although I have 4 columns. The rank is 3. Now you might say, well, does it mean that you only have 3 independent columns? Because clearly I have 3 independent rows. But do I also have 3 independent columns? Because I said this rank is the dimension of row space, but that's also the dimension of the column space. So it means in my column space, I have 4 columns, but only 3 of them are linearly independent from each other. The last one will depend on the rest of them. Is that the case? Well, of course it is. I can select, let's say, this guy here, and by a combination of these 2 other columns, if I call it C1, C2, C3, and C4, can definitely make C4 by a combination of C1, 2, and 3. And the reason for it is these guys, only a combination of C1, C2, C3 will form a 3D space. Clearly, there are 3 linearly independent columns. I can see if I just put them. So a combination of these 3 will form any 3D vector, and one of those 3D vectors can be C4. So definitely C4 can always be written as a linear combination of C1, C2, and C3. There is no doubt about it, right? And you might say, well, how can that be? Well, the coefficients are not hard. All you need is to solve for the system of equations here. If you solve, it will give you, let's say, x plus 2y plus 4z equals 3. And then it will give you y plus 3z equals 2 and gives you 11z equals 20. And these x, y, z are the linear coefficients that you need to combine C1, C2, C3 to get you C4. And it's not hard, right? You clearly see z is 20 over 11. Plug it back here, backward substitution. You'll get y to be 60, 22, so that's negative 38 over 11. And then plug both of them back into the first one, correct? That should give you some x value, which is basically 33. Correct? So this is going to be 33, and then minus 2y, which is 76, and then minus 4z, which is 80, right? And if you subtract, you'll get 29 over 11. So basically it means what? It means the last column C4 can be written as 29 over 11 first column minus 38 over 11 second column and plus 20 over 11 third column. So you see the fourth column is not linearly independent from the rest, only these three are. And so the rank of the column space is also 3, okay? So hopefully this example cleared up for you why the rank cannot exceed the minimum of the dimensions of the matrix and why the dimension of row space or the column space, in this case, both of them are equal to the rank. Good. So as I said, now I have something called range, which is the same as the column space, and then I have something called the null space. So range or range space, you might call it. Range space and null space. What are they? By the way, the null space also can be called the kernel of the matrix. What is nullity, and then what is the Rank-Nullity Theorem? So these are the last part of our lecture. So what are they? So let's go ahead and talk about it. So we talked about the rank, so we are good about that. Now what is range space versus the null space? So range space means what? Range space of matrix A, okay, is equal to what? Is equal to basically the column space of A. And column space of A means any linear combination of the columns or the space spanned by the columns, right? So it is going to be C1 A1 plus C2 A2 plus all the way to Cn An. So any vector U of such format where A's here, these vector A's are columns of A. So your A matrix is these columns A1, A2, all the way to An. And this A matrix can be in general what? M by N. So it means each one of these vectors is what? Is an M by 1. Correct? So the space of vectors M by 1, which is a linear combination of the columns of A, right? That can be called the range space of A, right? And this can also be written as, if I want to write it this way, I can also write it as basically a coefficient matrix C times A, where this is C1, C2, all the way to what? Cn. This is called what? U. correct? So this coefficient vector, not matrix, although vector is a matrix, this coefficient vector C1 to Cn multiplied by matrix A is U. This is the definition of the column space. Any vector U that is acquired by multiplying a bunch of coefficients C1 to Cn to the matrix A, that is what we call a vector in the range space of matrix A, correct? So clearly this guy here is an m by n, this is an m by 1. Now here you see it's not gonna happen like this, because if you call this n by 1, this clearly is not going to be multipliable. So although that looks like this when we wrote A's as columns of A, but now the dimensions don't match. So a better way to write it is actually write it this way. Bring A to the left side. So write it like this. Then now you have m by n. And you have, but you need an n by 1. This is a 1 by n, so what you need is a transpose, right? And this is going to be an m by 1. Or you can say U is what? A times a matrix C, or X. Some people use it X, so let me use X. So X are the coefficients here, correct? So any vector y that can be written as A times a coefficient vector x, right? This is going to be, this y is going to be in the range space of A. Good? Now on the other hand, if this vector of coefficients x or c, whatever you want to call it, so this x is the same as c. If you want, you can call it C, again, to avoid confusion. Let's call it just C. If all of the coefficients in this C are all 0, then you'll, of course, get what? Y of 0. But that's not necessarily the case. There are some scenarios that you saw the columns of A are what? Not linearly independent. All the matrix is rank deficient. So a combination of columns of A without all coefficients being 0 still can give you a vector of 0. That combination, those C's, we call them, they are in the null space of A. So if I get A times C to be equal to a vector 0, then we say what? C is in the null space of A. In this case, we say what? We say C is in the range space of A. And here you definitely need your y vector to be what? Not equal to all zeros. In this case, you do need all of the entries in y to be 0. Correct? So if I multiply matrix by a vector, if the result is not all zeros, we say that vector is in the range space of A or column space of A. If I multiply A by a column vector and I get all zeros out, we say C is in the null space of A. And again, it can only be, you can only get such a thing when the matrix A is what? Rank deficient. When there are some combination of the columns which can give you 0 without all coefficient being 0. So for example here, if I go back to the same example we solved, here I'll try to reduce the rank a little bit, right? And for that, I'll try to, I can also reduce the dependency of the rows instead of columns. So let me go ahead and do a little bit modification to this matrix and redo some operations, see what happens. So if I say this is 4 times, let's say, yeah, like 2 times first one plus second, or 3 times first one plus second one, then you will get a 2, a 6, a 14, and a 10, correct? 3 times that plus this one. So now take a look here. I'll try to do what? Row 2 plus row 1, fine. Now row 3 minus 2 times row 1. Let's see what we get. Row 1 stays, row 2 stays, good. We need to change row number 3. So you will get a 0 here, and then 2 times that, so you'll get a 2. You'll get 6, and you'll get 4. So right off the bat, you can see here what's going to happen, right? Look at these last 2 rows. They are identical. So if you basically just multiply it by 1/2, and then say here, when you do so, just 2 times row 2 minus row 3, you'll get what? You'll get all zeros, right? So let me do that for you. So what do you get? You get all zeros here, right? And rank of A is clearly 2. Now, if you now look at the columns, clearly now there are scenarios, there are combination of the columns where A multiplied by something will get you 0 without that something vector is all 0. Because really now you have only 2 columns in A that are independent. These 2 can easily be formed by a combination of the first 2, right? So you can definitely get A multiplied by a bunch of coefficients, non-zero, and still get you all 0, 0, 0. So here, if I call these 4 columns C1, 2, 3, and 4, you might say, what combination? Well, one easy combination here, as you can see, is I just add columns 1 and 3 and subtract from 2 and 4. So like 1 times C1 minus 1 times C2 plus 1 times C3 minus 1 times C4. Okay, if you do so, what will you get? Just add the numbers, but positive, negative, positive, negative. You will get a 0. Again, positive, negative, positive, negative. You'll get a 0. The last row is all zeros. So you see, I could get a simple combination of columns to get a 0. So if I now form my vector x, which is these 4 coefficients, 1, negative 1, 1, negative 1, when I multiply A by this x, the result is what? The result is all zeros. Therefore, I say this vector x is what? It is in the null space of matrix A. Correct? Okay, so that was finding, let's say, a vector in this null space. But is that it? Is there any other vector that I can basically use instead of this x, and I get what? Again, a times x to be equal to 0. So the answer is yes, there is. If you look at the second column, let's say, and the third column, they are clearly what? Linearly independent from each other, because third column is not an integer multiple of any multiple of the second column. So these two are clearly linearly independent from each other, and if we just neglect the first column, so basically multiply it by a 0, I can definitely combine second and third column to get what? The fourth column, right? So all I need is basically write it like 0, K1, K2, and 1, right? So K1 times C2 plus K2 times C3 becomes equal to what? K4, or if I multiply K4 by a negative, the result is what? 0. So X can be something like this as well. All I need is K1 and K2, and that's not really hard to do, right? All I need to solve for is such a case that you have 2 and 4, 1 and 3, the coefficients, and then the right hand side 3 and 2, right? All you need is to just convert this to the row echelon or solve this 2 by 2 system of equations. And here if I swap the rows 1, 3, 2, 2, 4, 3, then I just multiply the first row by -2, subtract from the second row, and I will get what? I will get 0, -2, and -1, correct? And that clearly means K2 times -2 is -1, so K2 is going to be 1/2. Then if you plug it back up to here, now you have 1 K1 plus 3 K2 is 2. So K1 should also be 1/2, I assume, right? Let's see. So that's right. This is right. Yeah, seems like both of them should be 1/2. And is that the case? If I add 1/2 of this and 1/2 of that, do I get 3? Yes, because that's 1, that's 2, that's 3. 1/2 of this, 1/2 of that, that's 1/2, 1.5, that's going to be 2. So as long as I can keep it like this, that will be another example. Or maybe I choose C2 and C4 as my independent and then combine them to get C3. Or I get C3 and C4, I get to get what? C2 as a linear combination. So in general, all I need is to get rid of C1, multiplying it by 0, choose one of these three, C2, 3, and 4, as a -1, and the other two as unknown coefficients, and then get what? Get to solve those two unknowns. So clearly, out of the 4 elements in X, I only have 2 of them to be found. The 2 others can always be considered as constant. So when I look at my null space, the space formed by vector X, this null space, has only 2 elements in it that I can freely choose. And so if we want to talk about the dimension of this null space, which by the way, we call it what? We call it nullity of A, that is equal to 2, the number of these 2 parameters I can freely choose. And that you can also see in this Rank-Nullity Theorem. In our case, we had a 3 by 4 matrix. The rank, I showed you, it was equal to 2. So the Rank-Nullity Theorem says the rank of A plus nullity of A, or the dimension of the null space, is equal to n, and n is the number of columns, which in this case is 4. So if rank is 2 and sum of rank and nullity is 4, clearly nullity has to be what? From here, nullity of A has to be equal to 2. And it is, as I showed you. Okay, so this Rank-Nullity Theorem is an important theorem that once you know rank of A and you know the number of columns of A, that you can find what? The nullity of A, or basically the number of independent parameters in that vector X to be chosen, right? So that's the idea of nullity that I mentioned for you, Rank-Nullity Theorem. And as I mentioned, the null space of A is also called what? The kernel of A. So here, instead of the null space, you can say what? the kernel of A, and the dimension of the kernel is also called nullity. So hopefully all of these important topics that we talked about in matrix were useful to you, and I will see you in my next lecture. Thank you.